All right, let's just jump right in. If I ask you, how old is the universe? I bet a number immediately pops into your head, right? It's a number you've heard over and over, one that feels, I don't know, totally solid.
Yep, 13.8 billion years. It's the textbook answer, right? The one we all memorize. It's nice and tidy, feels comfortable. A neat little fact we can just tuck away.
But is that really the whole story? What if I told you that number is just the tip of the iceberg? That, depending on how you ask the question, or maybe even what you're asking, the answer could be completely different, like wildly different. Or maybe, just maybe, the question itself is the problem.
So that's what we're going to do. We're going to peel back 4 layers of this cosmic onion. We'll kick things off with a hard, observable evidence. Then we'll get a little weird and reframe reality itself. After that, we'll recalculate time from a totally new angle. And for the grand finale, we'll ask the biggest question of all. Does time even exist at the deepest level? Okay, so first things first, let's start with what we can actually see and measure. Ground ourselves in reality. How in the world do scientists even come up with that 13.8 billion year number? Well, it all boils down to one thing: measuring how fast the universe is expanding. And right away, this is where we hit our first snag. See, our 2 best ways of measuring cosmic expansion, they don't agree at all. When we use the Planck satellite to look way back at the early universe, the data points to an expansion rate that gives us an age of about 14 billion years. But when we look at the late universe, the stuff closer to us, using supernovae, the expansion looks faster, and that gives us an age closer to 12.9 billion years. This whole mess is called the Hubble Tension, and honestly, it's one of the biggest headaches in cosmology right now. It's screaming at us that we need some other way to check our work. So how do we get around that? Is there a more direct way to tell time? Well, yeah, we can look for cosmic clocks. Think about it. The oldest stars, right here in our own Milky Way galaxy, are like these incredible ancient timekeepers. We can study their light, see where they are in their life cycle, and figure out their age. And the best part? This method is totally independent of how fast the universe is expanding. And what do these stellar clocks tell us? Well, a super precise, recent analysis looked at thousands of these old-timers, using data from the Gaia satellite, and it found that the absolute oldest ones are at least 13.8 billion years old. This is huge. It's a solid, observational anchor for us. Because look, whatever else turns out to be true, one thing's for sure: the universe can't be younger than the stuff inside it. So that 13.8 billion year number, it looks like a really solid floor, a minimum age.
All right, so we've got our anchor. We're grounded. Now, let's get weird. What if that 13.8 billion years isn't just about how long the clock has been ticking? What if it's pointing to something way deeper, something about the actual geometry of reality? There's a new theory out there that's asking us to completely rethink, well, pretty much everything: space, time, and even mass.
And the way to wrap your head around this is to start with something we all learned in school, the Pythagorean theorem. A squared plus b squared equals c squared. It works perfectly on a 2D flat surface, and you can easily extend it to 3D space. Then Einstein came along and did something incredible. He extended it to 4D spacetime by bringing time into the mix. So this new model, it proposes taking one more absolutely wild step, adding the mass of the entire universe as a 5th dimension, treating it just like length. It even uses fundamental constants to literally convert kilograms into meters. The fallout from this idea is, well, it's profound. In the standard model we're all used to, mass is just a fixed amount of stuff that happens to be in the universe. But in this 5D model, mass is an evolving dimension of the universe itself. And here's the absolute kicker. When you do the math, this wild geometric model independently calculates an age of about 14 billion years and a total mass of 10 to the 53rd kilograms. That is almost exactly what the standard model predicts. So you get the same answer, but you're describing a completely fundamentally different reality. Okay, so we've looked at a geometric view that seems to back up the number. Now let's go on the attack and challenge the number itself. And we're going to do that by questioning something we take completely for granted: the idea that a year way back then is the same as a year right now. See, the standard age of the universe, let's call it the EAoU, is based on this idea of a hypothetical observer who's just floating along perfectly still with the cosmic expansion. But what about us, real people on Earth? We're looking back in time through a universe that used to be insanely dense. And what does Einstein's general relativity tell us? That time slows down in dense, high-gravity environments. It's called time dilation.
So this new idea, the effective age of the universe, or EAO, recalculates everything from our perspective. It takes into account that from where we're standing, those early cosmic years were stretched out. They lasted a lot longer. So, what happens when you do this recalculation? It means the total amount of clock time that has passed from our point of view isn't 13.8 billion years. It's, get this, closer to 44 billion years. That's a huge difference. It means that from our vantage point, the early universe had way more time for stuff to happen than we ever thought possible.
And why should you care? Well, because this might just solve one of the biggest puzzles in astronomy right now. The James Webb Space Telescope keeps finding these huge, chemically mature galaxies way back in the early universe. Galaxies that look like they shouldn't exist. They seem impossible. Under the standard clock, a galaxy like JWST Z14-0 had just 280 million years to get its act together. But in this effective universe picture, that same galaxy had 3.7 billion years of clock time. That's more than enough time for generations of stars to live, die, and seed the galaxy with heavy elements. And you solve the puzzle without inventing any new, crazy physics.
Okay, so we've recalculated time and found a lot more of it. We've reframed it as part of the geometry of space, but for our final layer, we have to go deeper. We have to question whether time even exists. We've gone from 13.8 billion to 44 billion, but what if the real age of the universe is just 0?
That might sound crazy, but it's the shocking conclusion you reach when you look at our most fundamental theories of physics. When you try to put general relativity and quantum mechanics together to describe the entire universe, time just vanishes. It completely disappears from the equations.
This is famously known as the problem of time, the big master equation that's supposed to describe how the whole universe evolves. It's called the Wheeler-DeWitt equation. It does the opposite. It predicts a universe that is static, frozen. It's a single quantum state where there is no before and no after, no sequence of events, no duration. The thing we experience as the flow of time, it's just gone from the most basic description of reality.
And believe me, it's not because people haven't tried to fix it. Physicists have thrown the kitchen sink at this problem, but every single attempt to get time back has failed. If you try to define time by saying, okay, this part of the universe is the clock for that part, you end up with completely contradictory versions of history. If you try to treat it as just a probability, you can't explain why we feel time passing, why things change. And even the clever workarounds, they all fall apart precisely at the moment we need them most, at the superquantum level of the Big Bang itself. It's just this deep, profound, unsolved mystery.
So, after all that, after this whole journey from a simple, solid number to this deep quantum mystery, what is the age of the universe? Well, the answer seems to be, it's a beautiful mess. It really, truly depends on how you look at it.
You want to be an observer? Then the universe is at least 13.8 billion years old. You want to be a geometer? Then it's about 14 billion years, but that number is really a measure of an evolving dimension of mass. You want to be a relativistic observer on Earth? Then you've experienced 44 billion years of effective time. And if you want to look from the perspective of fundamental quantum reality, well, then the universe has no age at all. It's timeless. It just is.
And that brings us right to the heart of it, doesn't it? We started with this one, simple number, 13.8 billion years, and we've ended up staring at the possibility that time itself is just a story, a really useful story we tell ourselves to make sense of things. So, which is it? Is time a real, fundamental feature of the cosmos? Or is it just something that pops up in our big, messy world, a stubborn illusion that completely dissolves the closer we look at reality? The answer, it seems, is still waiting for its moment.